Alright, so next, continuous functions. So now using the notion of limits of functions, we can define continuity like this. So first we would need a function. So let x be a subset of R and let f be a function defined on x, that is f has x as its domain. Also let x naught be a point in x. Then we say f is continuous at x naught if the following happens. That is, if that limit exists and is equal to f of x naught, is equal to the value of the function at x naught. If that happens, then we say that f is continuous at x naught. We say f is continuous on x on the entirety of its domain, or if the domain is understood, then we also say that f is just continuous. If it is continuous at every point of the domain. In that case, we say that f is continuous. If f is not continuous at x naught, then we say that it is discontinuous at x naught. Now let us have a closer look at this definition. So we are defining continuity of a function whose domain can be any subset of the set of real numbers. That is the usual kind of function that we also consider while defining limits. Then the point at which we check whether it's continuous or not is it must be a point in the domain itself. And then the condition is that this limit of f at that point x naught in the domain x should exist, and it should be equal to the functional value of the function at that point x naught. Now does it make sense? You see, for the left hand limit to make sense, this x naught must actually be what? Do you recall? In the definition of limits, we require this point at which we are finding the limit of a function to be an adherent point of the set over which you are considering the limit. Now because your point x naught is coming from the set x itself, so automatically x naught is an adherent point of x, that is, it belongs to the closure of x simply because it is a point in x, it's an element of x. So that's why the limit makes sense, and the right hand side also makes sense because x naught is lying inside the domain. So f will have some value at x naught. And of course, if this continues to happen at every point in x, then we simply say that if the function itself is continuous on x, and if you do not want to mention that part on x, you can just simply say f is continuous. And if it is not continuous at some point in its domain, then we say that it's discontinuous there. So let us now see some examples. Because continuity is defined in terms of limits, so all the properties of limits that we have seen in the previous sections will be applicable here. In particular, the sequential formulation of limits will be applicable here. We are going to those things, but let's see some examples first. So in this first example, we are going to consider the very simple constant function. Say you have a real number c. We have already then considered this function whose domain is the entire set of real numbers, but the function maps every real number onto that fixed real number c, which is why it's called a constant function. And for such a function, we already know that no matter what real number x naught we choose, this limit always exists. And it is actually equal to c. Okay, we have seen this in the previous sections. But c also turns out to be equal to f of x naught by the definition of f. So f is continuous at x naught, and since x naught is any real number, so f is continuous on R, or just simply it's continuous. Okay, so any constant function is continuous. You can change c here, of course, getting another constant function that will also be continuous everywhere. The next one is also very easy. It is the identity function. We also know the identity function. Just like constant functions, it also has the entire set of real numbers as its domain. But here the definition is this. The function is no longer constant, but it does not change the input. It gives the input back as output. For this function also we know that corresponding limit. That's why we handle limits of functions first, and then we are defining continuity in terms of limits. And the thing that we know is this. No matter what real number x naught or x0 we choose, this limit of the identity function is known to be equal to that point x naught, which also by the definition of f is equal to the functional value at x naught, and that is why This identity function is also continuous at x naught, and hence it is continuous everywhere on R, or f is simply continuous. That's it. So any constant function is continuous and the identity function is continuous. So these are two examples. But now let's see some, I should not say non-examples, but an example which of a function which won't be continuous everywhere. This also is going to come from the previous sections, the signum function. And so this will be what is 944. We already know this function Sgn from R into R. Although we know it, but let's see once more. It's defining rule. We defined it to have the value 1 if our input is a positive real number. We defined it to have the value 0 if our input is 0, and -1 if our input is a negative real number. Okay, then this is continuous at any non-zero real number. An example is, say you want to verify its continuity at the real number 1, say. Then you can do that very easily. And all of these conclusions about continuity or lack thereof of these functions, actually we are able to say, conclude these things so readily and so quickly because we have already seen what the limits of this function are, okay, in the previous section. That's why. For example, what is the limit of this function at, say, 1? You remember in the section on limits, there is a result which has been given the name limits are local. That is, if you have one such limit, if you are looking at one such limit and it exists, then you can, instead of considering your, instead of focusing on the whole set on which you are going to find the limit, you can shrink your focus. Okay, you can focus in a small region around that point 1. So we can do that in this case like this. If this limit exists, then this next limit also has to exist and has to be equal to the above one. So the thing here is, let me just draw a small figure. It is like this. You have your 0 here, and on that side we have 1, some distance away from 0. Now, when we are considering this limit, then our x is varying over the entire set of real numbers. But now what we have done, we have narrowed our focus on this small interval with 1 as its middle point. And what is the, how far are we going on either side of 1? A distance of 0.1, which is why this left boundary point is 0.9 and the right boundary point is 1.1. Now you see that if you are, let us forget about that limit for a moment, let's just look at this one. Why are we doing this? We are doing this because we are actually allowing x to be close to 1, right? We actually want to see what happens to the functional values when x is close to 1. And because we want x to be close to 1, we can conveniently remove this part which is problematic for us. Why? Because at this point the functional value is 0, and to the left of 0, if you go on the left side of 0, then the functional values are constantly -1. However, at 1 and near 1, the functional values are constantly 1. So these are different behaviors. In order to see what happens near 1, of course, we need not consider these behaviors. That's why we have narrowed our focus on this part, which is also allowed by that result, that limits are local. Now, does this limit exist? Yes, of course it exists, because if you now look at the function sgn of x on this interval, then it's actually nothing but the constant function 1. So it's like that function f of x equal to c with c equal to 1. And we know that that limit exists and it's equal to 1. So that means this limit exists and its value is 1. So by the result that limits are local, this also exists and its value is also equal to 1. So that's how we are getting 1. But 1 is also the value of sgn function at 1. So that's why these steps show that the function sgn is continuous at 1. But that of course is only one point. But you can in fact understand quite easily that this same type of argument will work for any positive real number. That's because you see 1 is close to 0. One can say that 1 is close to 0. What would you do if you are really very close to 0? Then also you will be able to find one such region which is sufficiently small that still that region has 0 to its left side and does not contain 0. So the same type of argument would then show that still that limit, limit of sgn at that point, say at this point, is also equal to 1, which is the value of the function at that point. So that's how you end up concluding that sgn is actually continuous at every positive real number. What would you do if you consider a negative real number? Same thing. You find a region or an interval with that point as its middle point sufficiently small that this one also avoids 0. Then the function sgn at this point will have limit equal to -1 this time, because this part of the function will be used and the functional value will also be -1. But that again says that sgn is continuous at this point. So that's why sgn is continuous at any non-zero real number. However, is not continuous or discontinuous at 0. And we also know the reason for this. It's because the limit of sgn at 0 does not exist at all. We have seen how in the section on limits of functions. So if the limit fails to exist, then no question of continuity. This does not exist. That is because that trick of narrowing your focus near that point at which you want to find the limit, in this case would not work. No matter how small an interval you choose with 0 as its midpoint, you are going to have one portion of the interval showing one type of behavior, more precisely giving one type of output, that is 1, and the other side will give you -1. So they will clash with each other, and that will not let this limit to exist. Okay, so it does not exist. So that's why the function is continuous at every non-zero real number, but fails to be continuous at this precisely one point, 0. Then there is another such example which where also the function fails to be continuous at precisely one point, but there is a slight difference. Well, okay, that comes after another one. Okay, let's just see this next one. This is going to be the fifth item. Here the function is that one which uses rational and irrational numbers separately in its rule. So the function is defined to have the value 1 if the input is rational and is it 0 or -1? Actually it does not matter, but still we have 0 here. If the input is irrational. Yeah, the state of discontinuity of this function is as severe as you can imagine. F is discontinuous at every real number. Can we see quickly why? You see, we have already seen this function and we have handled those corresponding limits also, but let's just see once more exactly why that is the case. Actually, in both the cases, by both the cases I mean that the point at which you want to check continuity or a lack thereof, it may be a rational number or it may be an irrational number. Say your x0 is a rational number. Okay. Now you consider this sequence. It is a sequence of real numbers which converges to x0 by the limit laws. Now note this, x0 is rational, n of course is rational, it's a natural number in fact, a positive natural number, and square root of 2 is irrational. So a simple argument tells you that all such terms, all the terms in this sequence are actually irrational numbers due to the presence of this square root of 2. Alright. So let us give some name also to this nth term. Say the sequence in general is denoted an. Now let us see what happens to the functional values of this sequential time. So that means from this we are having this fact. Limit of this sequence an is x naught. However, what about this? Because all the an's are irrational numbers, so the functional values are 0. In other words, here we are looking at the constant sequence 0, and that converges to 0 of course. However, this is not equal to f of x naught, because x naught itself is rational, so f of x naught is 1, and hence by the sequential formulation of limits, this limit does not exist. By saying that limit does not exist, I mean this limit does not exist. Here we have limits of sequences, but the limit of the function does not exist. This limit does not exist. So if it does not exist, then no question of the function f being continuous at x naught. That means the function is discontinuous at every rational number. Alright, now let us consider the other case. Suppose now that x naught is irrational. In this case also the corresponding limit will not exist. However, the sequence now that we have to choose has to be chosen slightly differently. You see, from the very definition or construction of the real numbers, we know that there exists a sequence Bn of rational numbers, a Cauchy sequence of rational numbers which converges to this irrational number x naught. Okay, that happens for rational x naught also, but it will be useful in this case. Now what happens to this limit? Because the Bn's are now rational, all of them, so their functional values, corresponding functional values are 1. So we are getting the constant sequence 1 which converges to 1. However, that is not equal to the functional value at x naught, because the original x naught is irrational, so its f value now is 0. So that's why in this case also this limit does not exist. So the function fails to be continuous at an any irrational number x naught as well. So that's why it is discontinuous at every real number. And now after this, that other example is coming, about which I was going to discuss then. Here also the function f is from r into r, and the rule for the function is like this. It is defined to be equal to 1 if x is non-negative. X can be 0 or positive, and is defined to be equal to 0 if x is negative. So at the point 0, at the input 0, it has that thing, jump discontinuity. We discussed, I think we talked about this a little, jump discontinuity, removable discontinuity, while discussing limits themselves. But anyway, so in this case, f is continuous at every non-zero real number by arguments similar to the previous part. Okay, you can treat the two cases where x is a positive real number and x is a negative real number separately. But at 0 it is not continuous due to a similar reason that we have already seen 2 or 3 times by now. However, I didn't write about its discontinuity at 0, but is discontinuous at 0. However, if one restricts the function, f to this interval, the set of all non-negative real numbers, then it is continuous everywhere on its domain. Of course is this, not the entire arc but this, and now it becomes continuous everywhere on its domain, even at 0. So this is a little different from what we had in case of that SGN function. Is continuous on this even at 0 also it is continuous. The reason of course is that you see the functional values at the positive real numbers are the same as the functional value at 0. That's why if we separate all the negatives and we get rid of them, we keep only 0 and the positives, then things are again, it's continuous everywhere. But in case of that SGN function, there was a different behavior at 0 which is not shared by any other input. To the right side of 0, everything, all the outputs are positive. To the left side of 0, they are all negative. Positive means 1 and negative -1. Alright, so now having seen that sequential formulation of limits, of course naturally continuity itself, because it is defined in terms of limits, will have some such formulations. So there are equivalent formulations of continuity, and this next proposition is about that. So the setup of course is just this. X is a subset of R and f is a function from x into R and x naught is a point in x. Then the following three statements are equivalent to one another. Statement A, f is continuous at x naught. Then statement B involves sequences. If an is a sequence in x, and again I am repeating, by this I mean that each term an is an element of x. That I write in short like this, is a sequence in x converging to x naught, then the sequence f of an converges to f of x naught. This is statement B. And statement C just simply it says what f being continuous at x naught means in terms of the actual meaning of limits, that is epsilon, delta, those things. For every epsilon greater than 0, so this statement C is basically just the definition of limits when the limit is that special kind of limit where you have continuity. There exists a delta greater than 0 such that the distance between f of x and c, in this case in place of L, a general limit, we have the functional value at x naught is less than epsilon whenever x belongs to x and the distance between x and x naught is less than delta. Although we can almost immediately see why these are equivalent to one another, but still we have to go through a proof, which however we won't do here, of course. We will do it in the exercises. And it is in fact I think the first exercise. Yeah, exercise 941. So we will see it there. Now there is a remark specifically about this part B of this proposition. Just like we know that we can use that part B to verify that a function is continuous at a point, we can also use, see, because of equivalence, just like B implies A, B implies continuity, A also implies B. Using that part, that A implies B, we can calculate some limits if we know that some function is continuous. This next remark is about that. So it will be remark 948. And the remark is just this: if f is known to be continuous at x naught and an, we are not writing in detail, we are just simply writing this. If an is a sequence converging to x naught, then f of an converges to f of x naught. So that means if you have a continuous function and you have a sequence given to you which converges to that point where it is continuous, then you have another such limit like this, which may be useful in some situations. Now, just like we have algebra of limits or arithmetic of limits, we can add and multiply functions. We have seen all these things. Then what happens to the limits of those combinations? Correspondingly, here also we have a similar result for continuous functions, which is proposition 9. And it's been given a name also, arithmetic preserves continuity. Alright, so we are going to talk about arithmetic of functions. That means we will need two functions this time. So again we start with a subset of R, but this time we have two functions f and g, both having that subset x as their common domain. And suppose x naught is some, okay, no, it's not in general R, this is x. Then the statement is just simply this: if both f and g are continuous at x naught, then so are the following functions: f plus g, f minus g, maximum of f and g, the minimum of f and g, and fg are also all of them continuous at x naught. We have kept the quotient of two functions for a separate line for obvious reason. The quotient, well, okay, I should not start the line like this. The quotient itself will make sense only if g does not vanish. If g never vanishes on its domain, then f over g is also continuous at x naught. Okay, and its proof also we will handle only in the exercises, but you can understand that it will be almost immediate from the similar one that we had about limits. So this is going to be the second exercise. So any arithmetic operation involving continuous functions will again give us continuous functions. And in general, see, whatever we are having here, whatever we are saying about x naught can also be said about all the points at in x, provided f and g are both continuous everywhere on x. In other words, if f and g are both continuous, just continuous on the entirety of x, then all these functions, plus, minus, max, mean, product, quotient, they will also be continuous on the entirety of x. For this one also there is this extra condition that is needed. Now this arithmetic preserves continuity is very useful for proving or concluding that some pretty complicated functions are continuous. For example, one can use this proposition to show that this function, say, is continuous. Say you consider this function, which is in the form of a quotient where the numerator itself is the maximum of two functions. One of them is x cubed plus 4x squared plus x plus 5, and the other function, let me write it here because of lack of space, x to the power 4 minus x cubed, and the denominator is x squared minus 4. See, the denominator is a polynomial. It becomes 0 precisely at minus 2 and 2. That's why we have removed them from the domain of G. So there is no problem with the definition of the function. It's a well-defined function. Now in order to apply this proposition, you just take any point C in the domain. You know that these functions, these polynomial functions are continuous at C, which itself, however, is coming from where? Where is that conclusion coming from? That again is coming from this proposition itself. You see, it goes like this. You know that the function which maps x onto x, that is our well-known identity function, is continuous everywhere. So that identity function will also be in particular continuous at C. Then you use this fact that the product of any two functions, continuous functions, is continuous. You use this fact not just once but twice. That will give you that this function is continuous, which is the product of the identity function, 3 copies of it, x times x times x. So this is continuous. Similarly, x square is also continuous, and this x of course is again the identity function. This function which maps everything onto 5 is a constant function, which also we know, we have already seen that it's continuous. Now if you multiply x square by 4, that is again just a function of this form, where one say g is x square and f is the constant function 4. Both of them are continuous. So their product is also continuous. And then the sum of all these individual continuous functions is by this part continuous. You have to apply it several times. In a similar manner, this other function x to the power 4 minus x cube is also continuous. And so the maximum of these two continuous functions is continuous. Just like that, the denominator is also continuous and is never 0 on this domain because we have removed minus 2 and 2. So by the quotient part, finally g is continuous. Now instead of using this proposition, just imagine how complicated it would be if one simply tries to use the actual definition of continuity itself to this function. So that's why this proposition is it's not just simply for the sake of a result that it's there, but it's useful, highly useful. But besides these, there are some other more complicated functions which also turn out to be continuous. Let's see. The next one is proposition 10. Exponentiation is continuous. It has two parts. This is part 1. So what it says is this. Let us first go through these results, then we will talk about why we bother so much about continuity. What is the big deal? Say A is a positive real number, okay? Then this function this exponential function is continuous. Do you remember that we really put a lot of effort in defining this function in steps? That is, first we defined what it means to raise such an A to a power where the exponent is a natural number. Then gradually we increased the complexity. From a natural number exponent, we then went on to integer exponents, then rational exponents, then real exponents. It is that thing. And there we always have the base as a positive real number. It turns out that this function is continuous. And this one also we will prove in the third exercise. But there is part 2 of this also. The base here is positive, but the exponent of course can be any real number, positive, negative or 0, rational, irrational, anything. Again, exponentiation is continuous. This is part 2. Here t is a fixed real number, any real number, but it's fixed, it's not going to change. And the function now we have, instead of having its domain as the entire R, It now is defined on the set of all positive real numbers. Range, of course, is R. Now this is the other exponential function. You can see the difference. Here the exponent is the variable, but here the base is the variable. But it does not matter which one is the variable, the base has to be positive. So here, because we can take any exponent, so that's why the domain is R. But here the base itself is the variable. So we have to restrict it to the positive side. This is also continuous, and we will prove it in the fourth exercise. But there is this next one which is much easier than these things. Absolute value is continuous. And the statement is just simply this: the function from R into R, which is simply your ordinary absolute value function, is continuous. Well, I did not write it here, but you understand that this is continuous. So this videos nowadays, I am not presenting it as a formal presentation of this thing, but it's more like a discussion, so I may not write everything. So this is continuous, and the proof is very easy. It's so easy that let us see now. You just consider this fact. You take any real number, then you can almost immediately see that the absolute value of that real number is the maximum of the real number and it's negative. However, these individual components are themselves continuous functions. The first one is just your ordinary identity function, and the next one is the product of the identity function and the constant function minus 1, both of which are continuous, so their product is also continuous by the previous proposition. And that's why the maximum of these two continuous functions is also continuous. In other words, our ordinary absolute value function is continuous. That's just it. That is the proof. And there is another one also, which is extremely important. You see, although arithmetic of continuous functions can handle many functions, but still you would also need to consider composition of functions, because you see, using arithmetics we won't get all the possible functions. We need to consider composition as well. So this will be 30 electric. Yeah. So not just arithmetic, but composition also preserves continuity. I will now write the statement, but I need ink. Actually, when we go through something in mathematics, whether some part of mathematics or some topic, this is how we should go through it for the first time. We don't care about the proofs of the result uh, in our first reading. We just go through what the results are and what they are saying. We see examples and we see how the results work in those examples. We should also see non-examples, that is cases, instances where the result does not work, or say something, an object which is defined in some definition. The example is not an example of that object. So all these things will give us a very good idea of what the things are. And then only in our second reading we go through the proofs in detail and see why exactly a given result is true, how it is true. We see those parts afterwards. And we do this back and forth, okay, not just once. Then only we have a rough idea of what is going on. And that's how things go. So here the statement is like this. So composition, so we would need two functions. There may be more than two, but for two functions we have the statement. So we now have two subsets x and y of R. Let me just simply express that fact by writing like this. Okay, understand that this means that x and y are both subsets of R. Now suppose you have a function f from x into y and a function g from y into R. The reason for such choices is clear, of course, because we are going to compose f and g. Now say f is continuous at a point in x. F is continuous at say some point x naught in x, and G is continuous at f of x naught. You see, it makes sense because f is a function from x into y. So if x naught is in x, then f of x naught will be a point in y. So we can impose this condition that g is continuous at f of x naught. Then the function g composition f will of course be a function from x into R is continuous at x naught. Okay, so this is the result which gives us continuity of the composition of two continuous functions. That is the point version, but if it turns out that f and g are continuous throughout their domain, then of course their composition is also continuous on all of x. You understand what I am talking about. And this one we will prove in exercise 5. And finally, this section ends with this example. It gives us a function whose continuity can be concluded only when we use this composition of continuous functions. So we know that this function is continuous. It's just simply a polynomial function. So using arithmetic of continuous functions, this is continuous. Then using exponentiation of, exponentiation, that result, this is continuous because the base 5 is a positive real number. So the function is well defined and it is continuous by that proposition. And that is why by composition of functions, this function h, which is G composition F, whose rule looks like this, is also continuous. And just like this, using a combination of composition and arithmetic of continuous functions, one can conclude in steps that this next function is continuous. Well, okay, the author has not called this one h, he has just simply called this G composition F. The next function he is calling h. And the definition of h has many things. All the possible types of functions have been stuffed into h. It is a quotient, and the numerator is this x square. I can write anything, but I should show you what is there in the text. So in order to conclude that h is continuous, you need to go through steps. For example, first you conclude that x square minus 8x plus 7 is continuous, and then you consider its absolute value, then that also becomes continuous. However, that comes from which part? Composition of functions. And then you raise that to this power where the exponent is square root of 2, and there you use exponentiation part 2. Okay, exponentiation is continuous part 2 because square root of 2 can be considered in place of that p. It's any real number. Actually, it need not be positive also, but here it is positive. And what about the denominator? It is continuous, but moreover, the denominator never becomes 0. So that's why, again, by that quotient part of the arithmetic, h is continuous. But in spite of all of these things, there still are some functions which are continuous, but we cannot conclude that right now. One such example is this. This also turns out to be a continuous function, but none of the results we have seen so far allows us to conclude this. We will have to wait till we get to chapter 15 in the next volume, I think, yes. There only we will be able to handle this function when we learn about logarithms rigorously. And also, if one considers, say, let me call it I, say. this function where you assume that x is positive. This also turns out to be continuous, although it's a different kind of function where there are two variables. Okay, so we are still somewhat far away from seeing how this is continuous or even defining continuity of such functions. So those things also will come, but it will take some time. So that's how this section ends. After this we have the exercises, of course, which we will handle in the community section. And our next upload is this coming Tuesday, and as usual, as per our cycle, we will go back to graph theory. So we are right now solving those exercise problems, as many as we can. So we will go to the community section on Tuesday and solve some graph theory problems. So with that, I end the video for tonight. So see you on Tuesday with graph theory. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.